difference, then they are called insulator of or passive dielectric materials. On the other hand, if they are used for charge storage, then they are called active dielectric materials. So this is active dielectric materials and passive dielectric materials. There are two types of dielectric materials. In dielectric materials, all the electrons are tightly bound to their parent molecules. It means we are not having free charges or we are not having free electrons. The forbidden energy band gap is very high. It is 3 electron volt. So that for electrons it is not possible to go to conduction band from the valence band, because the energy gap, we can see that the energy gap is very high. It is 3 electron volt. So electrons cannot go to the conduction band from the valence band, and therefore it works as an insulator. Even if we are providing high temperature or we are giving voltage, the electrons will not go from valence band to conduction band. So dielectric are non-metallic materials of specific resistance and negative temperature coefficient of temperature. What is meant by negative temperature coefficient of resistance? So if we are increasing the temperature of dielectric material, the resistance will be decreased, so that we can say that it is having negative temperature coefficient of resistance. Now we are going to see the structure of capacitor. Capacitor is nothing but it is having, I said that it is having 2 plates, and in between that 2 plates a dielectric material is used. Here we can see that a dielectric material is given as yellowish thing, and the 2 plates are there. The plate area are called as A or known as A, and the separation or the distance between the 2 dielectric plate is D. So this is the basic structure of capacitor. Now we are going to see how does capacitor stores a charge. We are going to write it. How does it stores charge? See, this is a capacitor with plate A and plate B. Here I am giving a switch, and here voltage source is given. Switch we can say K, and voltage source. This is the positive end of the battery, and this is the negative end of the battery. See, when the switch is closed, then the electrons from plate A will move towards the positive end of the battery, and when they reach to the negative end of the battery, they are repelled to the plate B. So ultimately the electrons are going from plate A to plate B, so that there will be potential difference between plate A and plate B. The potential difference between plate A and plate B will keep on increasing by giving the voltage. Okay, so we will have some potential difference between the 2 plates. Now the question is that for how much time the electrons will move from plate A to plate B. Suppose we have given 10 voltage, the EMF is 10 volt. So when the potential difference between the 2 plates will be equal to the EMF of the battery, then the movement of the electrons will be stopped, and we can say that our capacitor is fully charged. So charging of capacitor is nothing but the electrons, the moving or the transfer of electron from one plate to another plate. So there is deficiency of electrons on one plate and increment of electrons on another plate, and therefore the potential difference will be increased, and after that if it is becoming to the EMF of equal to the EMF of the battery, then the electron movement will be stopped and our capacitor will be fully charged. So this is how our capacitor stores a charge. You can see the symbol in the PPT, the symbol of the capacitor, and we have the example of capacitor. These kind of capacitors are available in market. So this is how our capacitor stores the charge. Dielectric material can be anything. We can use glass as a dielectric material, we can use ceramic as a dielectric material, we can use plastic film, we can use paper, we can use mica, we can use these things as a dielectric materials. Capacitors are widely used as part of electrical circuits in many common electrical devices. As I said earlier, that capacitors are having many applications. So they are used in many devices, in many circuits for different kind of purposes. Capacitor stores energy in the form of an excess of electrons on one plate and deficiency of electrons on the other. We have seen in the example that the electrons were moving from plate A to plate B. So there is an excess of electrons on plate B and there is an deficiency of electron on plate A. So the potential difference will be there. After that, the time of storage may be in terms of nanoseconds, milliseconds, seconds or minutes. We cannot say that the specific time will be there. The capacitors can take time of nanoseconds, milliseconds, seconds or minutes. Sometimes it takes hours. A capacitor's ability to hold charge is measured in farads as we discussed earlier, and mostly capacitors are rated in microfarad or less. It is rated as nanofarads, it can be rated as microfarads. Now what is capacitance? So if a potential difference of V volts across a capacitor's plate causes Q charge to accumulate on its plates, then it has been found that Q is directly proportional to V. It means that the charge is directly proportional to the potential. So if the potential is increasing, if we are increasing the voltage, then the accumulation of charge on capacitor will also increase. Here we can put a constant which is known as capacitance. So Q is equal to C into V, where C is the capacitance. So that we can conclude that C equals Q by V. The capacitance of a capacitor is equal to the charge by the voltage, or we can say that the ratio of electric charge to the voltage is known as capacitance. So it is a very basic formula and it is very important formula if we are going to calculate capacitance, or if we are going to calculate electric charge, if we are going to calculate the potential, then this is very basic formula, that Q is equal to CV, or we can say that C is equal to Q by V. Different arrangements. Which are the different arrangements? First of all comes parallel plate capacitors, in which we have only one dielectric material, so it is known as parallel plate capacitors. The two plates are parallel and in between one dielectric material is there and voltage supply is given. After that comes parallel plate capacitor with composite dielectrics. What is meant by composite dielectrics? Composite dielectric means the parallel plates are having 2 or 3. It means that if we are using more than one dielectric material, then the capacitance of a capacitor will be different according to the relative permittivity of that materials, distance between them, and all these things works. So the second arrangement is parallel plate capacitor with composite dielectric materials. After that comes parallel plate capacitor with medium partially air. It means that we can use air as a material, as a dielectric material, and then we can calculate the capacitance. And then we can use multiple capacitors. It means more than one capacitor will be used to count the capacitance. So we are having these 4 kind of arrangement: parallel plate capacitor with composite dielectric materials, parallel plate capacitor with medium partially air, or multiple capacitors. These four things are having different equations for capacitance. For an example, we can see that how it is capacitance of a parallel plate capacitor with uniform dielectric medium. The dielectric medium is uniform. We have already said that the electric field density D is equal to psi by A. Here we can say that psi is a charge, or we can say electric flux is known as psi. So flux per meter square or coulomb per meter square, this is electric field density, and after that comes electric field intensity, which is V by D. We have measured the relation, or we have given the relation D is equal to epsilon 0 epsilon R into E. It means that the electric field density is equal to the absolute permittivity, after that the relative into the relative permittivity, and into the electric field intensity. We already know that D is equal to Q by A. So by putting the equation Q by A is equal to epsilon 0 epsilon R, and we can put E is equal to V by D. So now we have equation Q by A is equal to epsilon 0 epsilon R V by D. Now we are interchanging the positions of V and A. We can do that, so that finally we have Q by V is equal to epsilon 0 epsilon R A by D, where Q is the charge which is accumulated on the capacitor, V is the voltage, epsilon 0 is the permittivity of, or we can say absolute permittivity, epsilon R is relative permittivity, A is the area of plates, and D is the distance between the plates. But we know that C is equal to Q by V, as we saw that Q is directly proportional to the voltage, and we concluded that Q is equal to CV, so that we can say that C is equal to Q by V. So finally we have an equation of a capacitance of a parallel plate capacitor. C is equal to epsilon 0 epsilon R A by D, and the unit of capacitance is farads. So here by this equation we can say that we have an equation C is equal to epsilon 0 epsilon R A by D. So the capacitance of a parallel plate capacitor, it depends upon epsilon 0 epsilon R, the area of between two plates, and the area of two plates and the distance between two plates. So if we increase the distance, if distance D is increased, capacitance C also increases. If the D is increased, capacitance is decreased. And if the area A of two plates is increased, then the capacitance C is increased. So that we can say that capacitance is proportional to the area between plates, and capacitance is inversely proportional to the distance between the plates. Here we can also see that the capacitance increases with increasing the surface area between the plates, as we discussed. Capacitance increases with decreasing the spacing between the plates. If the distance is too long, then the capacitance will be less, and if the distance is short, then the capacitance will be more. And the third thing is that capacitance increases with increasing the relative dielectric constant of the insulator between the two plates. Here now we are going to see capacitors in series. Consider three capacitors having capacitance C1, C2 and C3. Here we can see that three capacitors are arranged in a series, in which we are giving a voltage V volts and a switch is also given. So the voltage of capacitor C1 is V1, the voltage of capacitor C2 is V2, and the voltage of capacitor C3 is V3. Remember that if we are putting capacitors in series, then the charge accumulated on each capacitor will be equal, but the voltage of each capacitors will be different. We have seen, or we can see that the resistance, if we are putting 3 resistance in series, then the current in the circuit will be same and the voltage will be different. Same here, if we are putting 3 capacitors in series, then the charge accumulated on each capacitor will be same and the voltage of each capacitors will be different. If the potential difference between 3 capacitors C1, C2 and C3 are, we can say, V1, V2 and V3. So here we can say that V is equal to V1 plus V2 plus V3, because we have put the capacitors in series. So the total voltage will be equal to the voltage across capacitor C1 plus the voltage across capacitor C2 plus the voltage across capacitor C3. So that we have an equation V is equal to V1 plus V2 plus V3. When the switch is closed, the 3 capacitors become equally charged. As I said earlier, that the charge Q accumulated on each capacitor is same. So we can say that the capacitors, 3 capacitors are equally charged. Now we discussed that Q is equal to CV. So that we can say that the V1, it means the voltage across capacitor C1 is equal to Q by C1. After that, the voltage across second capacitor can be given as Q by C2, and the voltage across third capacitor is given as Q by C3. Here we haven't taken Q1, Q2 and Q3 because we know that the charge accumulated on each capacitor is same. Therefore we are only referring Q for that. So that V1 is equal to Q by C1, V2 is equal to Q by C2 and V3 equal to Q by C3. Before we see that V is equal to V1 plus V2 plus V3, so we can write the equation V is equal to Q by C1, which is V1, plus Q by C2, which is V2, plus Q by C3, which is V3. So we have an equation V is equal to Q by C1 plus Q by C2 plus Q by C3. After that we can take Q as a common, so that we can have V is equal to Q and 1 by C1 plus 1 by C2 plus 1 by C3, and then Q